talking about transmission of mechanical power. Then we looked at the video on gears. Talked about terminology. Radial and actual loads. This will be on the test. So I brought a fidget toy. So an actual load is a load that's in parallel with the shaft. So this would be an actual load because it's in parallel with the axle. This will be a radial load. It's perpendicular to that. Actual load, radial load. Yeah, so it's perpendicular with the radius. So the radius of a circle goes out from the center. So that's why you can remember. The radius goes this way. And then if I point toward the axle, so what a wheel mounts on, we call that an axle, right? So if you think about your back tires have a lot of axle load on them. And then your front tires have both loads because you turn your front wheel.
So a ceiling fan would be
Yeah, so no, ceiling fan is this way. So if it's this way, this is parallel. This is parallel with the axle. So this is an actual load. This is a radial load. Think about the radius of a circle. What does the radius of a circle do? It comes from the center and goes out. So here, my load is this way right here. So we call this is called a radial load. And this is putting weight on the axle itself. Right? You understand? So this is axle load. So radial loads are what? Perpendicular to the shaft. Axle loads is parallel with the shaft. You understand that? I like axles on the car, right? Your front wheel not only got an axle load, it's also got a radial load. Because when you turn, the outside wheel is literally trying to do what? It's trying to go this way. Right? You understand? And of course your inside wheel is going this way. But, the rail wheels though, they basically, have a lot of radial load. So if you looked in the bearings on the real wheels, you would see those are just standard ball bearings. But if you looked at the bearings on your front wheel, those would be what we call brush bearings. We'll look at those. I don't know if anybody's ever repacked their front wheel bearings, and looked at those and pulled them out. But I used to do that kind of stuff at home. So these are different types of gears. So we have what we call spur gear. This is probably the one that's most out there. It's probably one of the easiest gears to make. These guys will handle a lot of axle load, right? Radial load. Depending on how they're mounted, but these guys, so they mostly widely used gears due to the simplicity used in transmitting torque between parallel shafts. Of course, we know that depends on which ones are driven and which ones the driver. Depends on whether it's a mechanical a torque multiplier or a torque divider, right? You understand that? So if we got a little wheel feeding the big wheel, then that's going to be a torque multiplier. Divider, torque multiplier. If the big wheel, the big gear feeds the little gear, then we have a torque divider that is speed multiplier. So how can we calculate mechanical advantage? We count T. Out driven in count the teeth, right? What's the other ways we can do it? We can do the diameter. So y'all can measure the diameter. Just do it the same way both times. So if you measure the outside of the teeth, make sure you do it on the other one. Or you can do the radius, either one. So you can calculate the advantage by knowing the number of teeth. right? You understand that? You can measure the diameter of both of them, okay? Or you can do the radius of both of them. And it's out over in, right? So that's pretty easy. This is the way we always calculate gain. How much do we get out compared to how much we put in? And then your speed multiplier will always be the inverse. So if you got the mechanical advantage and you wanted the speed multiplier, you just take the reciprocal of and that will give you your speed. So these are helical gears. Are used in transmitting torque between parallel and non-parallel shafts. They are not as noisy as spur gears, and they can handle a greater amount of torque because you have more surface area in your teeth. The only problem we have with helical gears, there's a lot of there's a lot of actual torque. These things want to pull themselves apart because of the slant of the gears, right? You understand that? So what they did, and you'll see these used a lot, these are called helical, double helical, so they noticed the slant's different in both of them. And so that way they compensate for each other on the radial leg. Right there. Well, a helical gear would, I don't know, that's a good point. I don't know, we can't see the gear. Can you see the gear? Can you actually see the gear? Oh, okay. It's got a helical gear on it? Well, it's got one of these, right? Oh, it's got one of these.
It doesn't look like that.
Oh, no, that's not a helical gear. We'll show you that. Herringbone basically is they take the two helical gears and they combine it on one gear. Of course, this will be a little harder to machine. Let's call it herringbone gear. Are we okay? These are bevel gears. Bevel gears, of course, is used to change the direction. I mean, not the direction, the angle. Are used to transmit rotary motions between intersecting shafts. These formed on a conical surface that seems to be straight or drillable. Or helical, I guess you should say. Huh? This is spiral, but it could be helical, which would be a slant. Yeah. They're calling it a spiral bevel gear, but I haven't heard call it.
I was looking at that one, those two are the same size as the one
This one, we have a little one here and a big one here, so you calculate depending on which one's the driven and which one's the drive. This one is hard to tell. To me, it looks like this is a little smaller than this one.
If they're the same size, though, it's just transfer.
Just to change the direction. Just to change the direction if they're the same size. That's a good point. We okay? I don't know if we got any of these or not. This is called a worm gear. These guys usually have a really, really big ratio between this is the driver and this is the driven. This guy right here is usually real big and this is real small. This is the one that he was showing on video. Where he had to do what? And it took, I forgot, like 40 turns for it to do what, make one revolution. These guys are usually used for really high torque. I've seen them up. There's one video where they're actually opening the locks on a canal somewhere. I don't remember what it was. But the guy pulled his boat up there and he jumps out and he cranks that thing. Of course, it moves real slow, which deals with a lot of pressure. So this is called a worm gear. If you notice, to get more contact, I don't know if you noticed in this one, you'll see this done a lot. But can you see what they're doing with this? They've actually got it wide. And what that does, that lets the driver go get more surface area with the teeth of the driven. You see what I'm talking about? Yeah. So if you look at this one, the actual driven is got this. The teeth has got this. And what that does, it lets the driver go what? Further in and get better torque. Modulus. So modulus basically tells us, we've got all different types of gears, but the modulus of the gear tells us if the two gears will mesh. Does that make sense? So if they've got the same modulus numbers, what that means is their teeth will match together. And small gear is the pinion, larger gear is the gear. Right? Of course, we got driven and driver too. I like that one. In most applications, the pinion is the driver to reduce the speed and increase torque. Gear set, this is two or more gears. We usually call them gearboxes, but that's technically they're called gear sets. The driver transfers torque and speed to the driven. So we know about those. Are we okay? This is called an internal spur gear. These are used to reduce the space of the gear. So if I've got one gear here and then one gear over here, this is going to occupy a lot of space, right? You understand that? But if we put the driver in the center like this, then this would only occupy the space of the driven, right? Does that make sense? First time I saw this was on a.
So is there normally another gear inside the circle?
Could be. It depends on where you put an idler gear in there, but we know what idler gears do, right? So if, and I think there's a video up there, but you're right. We come over here, we can do this, and then we can put a gear right there. Well, this would be considered an idler. It would not have anything to do with the torque or the speed, right? Does that make sense? Yeah, an idler gear is a gear that we use idler gears for basically a couple of reasons. One would be to increase the distance between the driver and the driven. Another thing we use an idler wheel is to change the rotation of driven. So we know if we mesh two gears together, then the driven would always be in the opposite direction of the driver. So if your driver was running clockwise, then your driven would be working counterclockwise. If we put an idler wheel in there, then what it does, it means your driven and your driver would go in the same direction. And it has absolutely no effect on the multipliers because it just cancels each other out. In the video, he actually did the math. So about the only thing we use idler wheels or idler gears for is to increase the distance between the driver and the driven. And it also allows the driver and the driven to spin in the same direction. That makes sense? And the size of the idler has nothing to do with whether it's a torque multiplier or a speed multiplier.
So it's like in that gear video, had the two bigger gears, and had one gear.
One in the middle, yeah. And he changed it out to a bigger one. And he did all the math, and it actually canceled out. It was a pretty neat thing. So yeah, the idler wheel basically has nothing to do with whether it's a torque multiplier or a torque divider. All it does has two purposes, and that's what? To change the spacing between the driven and the driver, and the driver, or to make the driver and the driven rotate in the same direction. So that's the only reason we use it for.
So the driven is a small.
No, it depends on whether it's a multiplier or not. So the driven is where we get our output from, take our output off. The driver is what our prime mover moves to, or from the next gear set. So the one that's pointing back toward the prime mover, and that's not right. The one that gets its input from a gear from the prime mover would still be we'll look at this in a minute, but still what we call the driver. And the ones that move toward the output, these are called the driven. Right now, it doesn't make much difference because we've only got two gears. But we're going to look at a gearbox in a minute and try to figure out, whether it's a speed multiplier or torque multiplier. So you got to figure out which one is pointing toward the driver and which one is pointing toward the driven. Does that make sense? So the one we got is pretty easy, and the one I show y'all is on the Siemens test. The Siemens level 1 test. So if we want it to be a torque multiplier, then your driver is going to be smaller than your driven. Anybody that's rode a bicycle, a 15-speed bicycle, understands it. So you're shifting those gears. You got gears on the front, which is your driver, and you got gears on the back, which is driven. And if you ever watch that thing shift, if it moves toward the big one on the front, then your bike goes faster. But it's harder to do it, right? And then on the back one, if it moves toward the little one, then your driver goes faster and moving around. So this is why you see these bicycle riders going up a hill and they're going like this, and the bike's going real, real slow. Because why? They're going from what? Little to big, right? You understand? So it's a speed divider, but a torque multiplier. Anybody ever rode when I had mine, that's all we did when we was in Japan, was bike. Everybody had bikes. So that's when they didn't have 10 speed. 15 speeds. They had 10 speeds. So I think now they have like a 50 speed. And you can see those gears moving around, or you just move that chain from, so your back goes from big to little, and your front goes from big to little. And then you shift them. Anybody have a 15 speed bike? 7 speed? That's probably mountain bike or something like that. Huh? 10 speed? Yeah. And you can climb hills with them, but you're not going to go fast. You know, you're going like this, right? Because you're doing a torque multiplier and not a, huh? They ride them around my neighborhood. We had a guy that came to school here that rode from Center Point every day on the steering wheel. Oh yeah, I drive it. That's good though. Yeah, Center Point. And he take night classes too. I was telling you. So saying which one's the big and which one's the little depends on whether it's a what, whether it's a torque multiplier or torque divider. For torque multiplier, the output's going to run slower than the input. A torque divider, the output's going to run faster. And this is true on just about all our drives, whether they're belt drives or gear drives. We measure input out over in, right? This is the ball and screw. We have one of these. This is what actually moves the carriage on the the second module. It actually moves that carriage. I think they call it the testing station, where they're actually testing the height. That's one of these right here. And you can actually see the trough that it follows. You can see it on the outside. The bearings on the inside actually rotate through that thing. So ball and screw converts the rotary motion into a linear motion with very little friction, able to transfer and withstand high thrust loads, minimum internal friction, high degree of precision. Disadvantage, they can drive back, so we would usually add an angle because they could drive back. So we definitely have one of these. I was going to, we got one of the motors that was on the Festo line that ran the belt down there. It's got a gearbox on it, but it's riveted in. I was going to get this, burn the motor. Did I show y'all that one where the brushes had worn out on it? Yeah. So I'm going to try to drive that so y'all can actually see the gears in there. So this is called a planetary gear. This is pretty cool. Can you see why it's called a planetary gear? So this is what, this right here would be an idle. And of course, this would be, an outside, inside view. Go back. Internal. You just spur here. So this would be a lot higher torque, right? Because we're doing more teeth at the same time.
So all three of those are idlers is just at once.
So all of them.
Okay, all of them.
So what we got instead of having a column, what's the driver? We got there are two inputs to the planetary gear, RPM or stone range. The output is the speed of the arm. I need to go back. We got a really good video somewhere, where, first, gearboxes they had on tanks used these planetary gears. And what they would do is, depending on what they were driving, so that it would shift the drive from the driver now. Or forward ratio, that's why I can't remember exactly how they do that. There's an old video. I need to go find that thing where they use the same thing what they used on the tank. A lot of times on the gears, though, if you ever notice, is the actual teeth will come up and then it'll angle and then it'll be like this. And then when it meshes, it won't go to all the, when it meshes, it won't go all the way down into the thing. Or they'll actually deliberately have a space in here. That's what I've seen. And of course, you can see why they angle them like this on the top, right? Because it makes the transfer when it moves in and out a lot smoother. With a pair of gear sets, power is transmitted by the force developed between the contacted teeth. So there's a lot more to gears than just the modulus. The modulus, this means that the gears will fit together. But then you got the pitch and all this other kind of stuff and how wide they are and all kinds of stuff that comes along with gears. We just don't have time to teach that. Gearboxes. So anybody ran into a gearbox before? Everybody has this. This is basically what your car has on it that shifts between the gears for you. So this is a typical 5-speed transmission. Looks like it's a manual transmission too. What type of gears does it have? Vehicle, right? See, they're at an angle. And basically what you do, so you're driving, I think this is the input, so this must be the out. This is from your engine connected to the back of your engine wheels. Of course, cars are now predominantly front wheel drive, right? And all it does is automatically do what? Shift between the gears. So calculate the ratio of gear teeth. So first of all, is this a torque multiplier or is it a speed multiplier? So here's my output over here. Here's my synchronous motor. So this is my input over here. This is my motor. So this is the motor shaft. So this would be our first gear. So is it a speed multiplier or torque multiplier? So what would be the ratio? What would be the mechanical advantage if Z is equal to the T? Huh?
Uh,
Yeah, I could say Z equals the diameter, or I could say Z equals what, I could say Z equals the radius, right? You understand that, in inches, it wouldn't make any difference, right? So we just said Z equals the gear T. But y'all understand, that can be anything, we can do it three different ways. What's the three different ways? We can do it by the number of feet, we can do it by the diameter, or we can do it by the radius. So everybody in agreement that this is a torque multiplier.
One to one.
Okay.
One side's a little bit. Because radio.
So is this a little fig to big?
Yeah.
Okay, is this a little fig to big? So all the one that goes back toward the drive is what? A little fig to big. So this is definitely a torque multiplier. Well, we're trying to figure out how much torque does it multiply. So how much torque would we get out of the first set of gears on the left? So we'll call it set one would be equal to 45 over 15. Is that diameter or is that radius or that T? Don't make any difference, right? You understand that? So we get a mechanical advantage of 3. Okay, over here, I got 48 out, 12 in. The mechanical advantage would be what? 4. So what would be my total mechanical advantage? These are gains, huh? Let's do it this way. So let's take this one and add it to that one. And then let's take this one and add it to that. So what was 45 plus 48 equal to? Huh? And then what was 15 plus 12 equal to? What's that? I think I'm doing this one. What's that? That can't. So this gives us the mechanical advantage of 3. This gives the mechanical advantage of 4. So if this right here was turning at, if this was turning at 1200 RPM, then what would it be turning down here? So what would it be turning right here? There's a 3. It's a 3. So is it turning faster? Are we going to multiply it by 3 or divide it by 3? So this would be turning 400 RPM. So then I got 400 RPM right here. And then we divide this by what? What's our mechanical? 48 over 12, what's that? 4? So what's it going to be turning out here? Okay, 100. So, oops, sorry. So I'm getting 100, oh, up here. So this guy here would be turning at 100 revolutions per minute. Y'all understand how we did that? Yes or no? Well, Well, if it's a times 3 torque divider, it's going to be a divide by 3 speed. You know, they're the opposite of each other, right? So we're trying to figure out what the total advantage is. So what we're doing is we're using speed. So we know it's out over in. So what's out over here? Okay, so we'll call this set 1. It's 45 over 15. What's the mechanical advantage? Okay, so if it's got a mechanical advantage of 3, then the speed would be equal to 1/3. They're the reciprocal of each other. They're exactly opposite of each other because we're getting the same work out that we're putting in, right? You understand that? So over here we said, okay, my mechanical advantage for 2, that's what I should have done, would be 48 divided by 12. What do we come up with? 4. So my speed, this is going to be a speed divider, is going to be 1/4. Alright? Everybody okay? Okay. So, I come over here and I say, okay, if this is 1200 RPM, then what's 1/3 of 1200 RPM? I made it up. I said, what if? If I say, what if this is 1200, I made it up. So that's a good question. Because it works out real easy for our multiplier. So that means I have 400 RPM right here. Okay. So that 400 RPM is right here. So what would be the speed out here? It's going to be 1/4. So what's 1/4 of 400? 100 RPM. So that means I got 1. So what's our torque? What's our torque multiplier? Is it 3 plus 4 or is it 3 times 4? So this over here is running 12 times faster than that over there. So that means the torque must be 12 times the input torque, right? You understand that? Yes or no? So this guy here's got a mechanical advantage of 4. So it means if I put 100 pounds of force over here, if I put 100 pounds of force over here, then I would get 400 pounds over here of torque over here. And we did speed because speed was easy to deal with, right? So if my speed is 1/4, then mechanical and mechanical advantage and speed are inversely right proportional. That means foot pounds, torque, you know, if torque, it would be foot pounds. So that's why we measure torque, right? So if I put 100 foot-pounds over here, I get 400 over there. Well, see, speed was real easy to work with, right? Because we know it's a speed divider. But if speed goes down by 1/4, then torque's got to be going up by what? By 4. So what we said is that I just took these two right here, so I had 3. Over here I got 4. So to get the total mechanical advantage, we'd say 4 times 3, or 3 times 4, equals what? 12. So you take the mechanical advantage of each gear set, and then do what? Just multiply them together. You understand that? Yes, no? Huh? This is on Siemens. I forgot what the test. I know this gearbox is. I'm not going to tell you what it is. It's a lot easier than what we do, by the way. I'm not going to give you the answer. So what you would do is you'd take the mechanical advantage of each set in your gearbox, and then you multiply them together. And then that would give you the total mechanical advantage of the entire gearbox. So you could do that on your bicycle. count the number of teeth on the output, on the input, and you can figure out all the combinations. So I think, so if you got 15 speed, that means you got 3 on the front and 5 on the back. I think that's what it is. So we okay. You want to change it up? We could do another one. I could change these numbers. Huh? It is, and that's what so you calculate the mechanical advantage for each set of gears, and then you just multiply the mechanical advantages together, and that will give you the overall mechanical advantage. You take the reciprocal of that, and it's going to give you the speed, right? You understand? Compared speed to output. So mechanical advantage and the speed is inversely proportional. So 1 over. If you know the speed, right, you can flip it around and it would give you the mechanical advantage. We use that so often that, like I said, a scientific calculator's got that on it. Because when you take the reciprocal, it gives you exactly the opposite. Ready to move on? Slip clutches. Engage and disengage the power transmission without stopping the prime mover. Cannot be used to control the amount of power transferred and motion. Can also be used. So we're using the slip clutch to set the torque, like on the torquing station. We're using the slip clutch to set the torque. On the carriage, the first carriage on the testing station, they use that because we jogged that thing we manually jogged that right and positioned it under the. So we're okay? Bearings. Has a lot to do with bearings. We're just going to get a basic look at them. The device they use to enable rotation of linear movement, by reducing mechanical friction and stress. Resembles a wheel. Main function is reduce friction and facilitate smooth rotation on an axis. So we use these things for a lot of things. Rotating fingers. Anytime we got to mount something. So these are definitely motors. Flame bearings, ball bearings, roller bearings, thrust bearings, and this video is up there, by the way. It's a good video. The guy explains things pretty in detail, especially when he gets into the different races that these things, self-aligning bearings and stuff like that. That's really good. The first time I saw a self-aligning bearing was when we was in Germany, where you could take the inside race and you could move the outside race around it. It was really cool. But the way the thing works. So we're okay on radial load and axial load, right? We're okay. This is really where it comes into play. Plane bearings. I was looking at this guy. By the way, it'd be hard to pass this around. I guess we can. So we looked at a motor called a brushless DC motor. And so this is a brushless DC motor. And I don't have my camera up. But this guy here uses plain bearings. So plain bearings are basically the sleeves that it goes through. So it don't have any balls, it doesn't have any rollers or anything that would be in a bearing. So I saw several of these out at US Steel. They grease them all the time. So usually they keep these things well greased. So this is a plain bearing. So, and I would like to shift the rotor around. We talked about a brush, which means the rotor itself is imagined. I don't have a camera hooked up, guys, and you take it. So I'm going to take a 2-minute break and let me get my camera up. Do it now. I thought it was. Oh, yeah, sorry, I tried to upload it, but it wouldn't let me do it for some reason. So I did try to upload it, by the way. And I'll get, so, this is a, brushless DC motor. So this would be the stator. And then it's got a Hall effect that actually senses the magnet when it's being sent through to set the speed. So plain bearings, pretty straightforward. Then we have the good old ball bearing, reduces rotational friction, supports radial and actual loads depending on the model. I thought I changed that, guys, but I need to redo that. Depending on the type. So like we did, we had radial bearings that self-align and they do the grooves in there differently to handle actual loads along with radio loads. But primarily they're really good for radial loads. So this is the parts of the standard bearing. What the unit rolls into either steel balls or rollers. Two metal inside rings and outside rings. These are used, most people call them races. Then you have a cage, which is basically a low friction metal ring that establishes the spacing of the actual rollers or the actual balls. We have a machine steel ball and then a inner race. So this is the basic makeup of all bearings that I know of. Whether they use steel balls or whether they use rollers, they would still be basically the same. So these are roller bearings. So roller bearings can handle a lot. So on a ball bearing, all we got supporting the weight is the part of the ball that's running inside the race, right? Understand? So what a roller bearing does, it has more surface area so we can handle heavier radial loads. So these are roller bearings. Yeah, this is silver. And they slope them, when they go into thrush bearings or bearings that's got a lot of, actual loads, it'll be smaller on one end, it'll be tapered. And basically it'll handle better, better actual loads. So you can see, roller bearings and ball bearings basically different compared to roller. We still have the outer race and the inner race. But the ball bearings, the only thing that supports the balls are the grooves. And they change those grooves around, by the way. Like we talked about, the ones that have misalignment, they slant up. The balls that you can move, the inner race and outer race can change the field. But the videos really good. Y'all need to go out and look at those. Those things are 10, 15 minutes a piece. We just don't have the time to show them, but they're all out there, up under in this section out there. I think somebody wanted the gear, but all of them. So these are thrush bearings. These are the ones that have that can handle high actual loads. These are the ones that you're using in your car right here. So they're literally put in there at an angle. And then of course the outside diameter would be smaller than the inside diameter. And you can see what they do here. They actually have grooves set up a little bit. Instead of the ball being mounted this way, they're mounted regularly. So these guys have a lot of and the races, instead of being out, the races are on the inside. And you can see this too. They don't show that, but this is very popular, where they'll come in and put a covering over the actual bearings itself. a lot of times they'll be metal. And then what they'll do is they'll put grease or oil in there, and it'll stay, it'll last a lifetime. And the bearings are slightly smaller, than the radius. So if you ever got one that's cold, you can really move this thing around a little bit. Because what they gotta do is bearings get hot, and what happens to metals when they get hot? They expand. And if it expands too much, then it's gonna, it'll cram in there and they'll freeze bearings. I've had that happen, where the bearings just weld themselves together. I've had this happen on my lawnmower deck before, where the bearings have actually welded together. So they got too hot, right? Beyond the limit, so. What's that? No, because you got a clutch on your lawnmower. It's just if you engage the blade, it could either burn your burn your belt up, or it could stall your motor. So yeah, if you can crank your mower and then when you engage the blade, if it stalls your motor, it could be bad. So what you're talking about? If the motor won't start, and it's not because of the deck, because you start, not unless you're trying to start the thing, and I don't know of any. Of course, somebody could override that. Most of these riding lawnmowers, they won't let you start it if the blades are engaged. The clutch that runs the blade. Roller chain. So what advantage does a roller chain have over gears?
System.
Yeah, that's one of the biggest advantages, the distance between the two gears. And what do you notice about the driver and the driver? I don't know which one it is. They turn into what? They turn in the same direction without an outlet. So the distance that we can put, we don't call these gears. What do we call these things? You know? Start with the S. Sprockets, yeah. So these are called sprockets on a gear. We calculate the advantage exactly. So the chain itself has nothing to do with the mechanical advantage. It's what? What we can use to count the number of teeth, or we can measure the diameter on this, and we can calculate the mechanical. So we calculate the advantage just like we do. So you could use the radius, you could use the diameter, or you could use number. So what's the problem we have with these? So these things have really good positive drive characteristics. They have no slip in them at all. But what's some of the things you're going to have to maintain on a chain drive? We're going to have to oil it. So if anybody's ever rode a motorcycle, it's got chains on it. You oil it. Most people buy these self-oilers, which is a little brush that runs across the chain and automatically keeps oil on it. Anybody that's had a bicycle knows what happens if you leave it out in the rain, right? What happens to the chain? And it welds itself together. You can't get it apart unless you soak it in oil for a long time. So, of course, then the width of the gears would determine, and of course, what you got to do is make sure you match the pitch of the chain with the pitch of your gears, right? So you just can't go out and buy any chain to fit anything, right? You understand that? So, advantage, transmits high torque levels in the small package, relatively low installation cost, readily available stock components, 95% efficient and installed correctly. Another thing you got to really watch out for on chains is that alignment of the chain. The chains have got to be aligned really, really well. I had a chain drive motorcycle, and the chains wasn't aligned exactly right, and it wore out the teeth on the sprocket. So I had to replace that. So you want it to run down the center, right? You understand that? And then, of course, we got to adjust the tension on these. So that was one thing that I had to do on my motorcycle, was the back wheel actually would move back a little. You use that to adjust the tension on the chain. So you had to do that every once in a while. So change wire. So, okay. 15,000, design, life, properly maintained, create, change, any link, disadvantage. We gotta do what? We gotta make sure they're what? In alignment. Slack. You gotta make sure the slack is right, right? Tension, you gotta keep the tension right. And of course the drive component. We okay? This makes sense? So most of us played around with things. Belts. So what advantage does belts have over chains? Huh? Flexible. Right. The alignment, we don't call, what do we call the wheels on the chain, on the belt rail? Pulleys, yeah, we call them pulleys. Yeah, cheaper. Right. Right, than your chain. It's more forgiving than, it's got a little slack in it, so it's more forgiving, like with motor stalls or something like that. A little more forgiving on that. It's not considered positive drive because there's always a little bit of slip, right, in a belt drive. So we wouldn't use this on something that we had to maintain a perfect speed or really, a good speed. We use either gear or we use either chain. So how do we calculate the mechanical advantage on these? We can't use teeth because they have no teeth. So how will we calculate that? Search for the diameter. We can use diameter, right? Or the radius, so we can measure that. Make it radius diameter out over diameter. So we have flat belt. Probably the most popular is we have synchronous belt. This is used a lot on automobiles. So what happens is the pulleys actually have teeth in it, and the belts are teeth, right? On those, so those are very popular. V-belts, these are probably the most popular out there. V-belts. These are a ton of places. Huh? These are used in a lot of places. V-belt. Either that version or this version, a notched V-belt. So what advantage does a notched V-belt? So what you do is your pulleys, instead of being straight up, the pulleys themselves would actually be slotted, right? And of course, then this would fit in the groove. And when we start these things up, a chain, there's not as much of a jerk to start up a belt drive there is for a chain drive. So what happens is the belt's sitting up there and it's kind of slack, and then you start it, it's got to do what? It's got to pull itself down and get into the groove real tight to create the torque. So it deliberately slips a little bit when you start something up. These notched belts, basically these guys here, they're more flexible, so they're easier to work with. I don't know if everybody actually worked with a V-belt. It's actually hard to flip them around and do kind of stuff, right? So notch belts are easier to work with. They're more flexible, which means our pulleys can be a little closer together. Plus they run cooler. So a notch belt runs cooler than a regular V-belt. Because the notches themselves actually picks up air when it's spinning, right? So the advantage of a notch belt over a standard V-belt, of course, is they're more flexible and they run cooler. And then we have multiply belts. These guys are basically variations of V-belt. And you'll see this a lot where they'll have multi-pulleys and then they'll have multi-belts running on the same unit. Well, they're doing the same thing. You get a lot more torque, right? Plus, if one of your belts break, you might still be able to do what? Until you can get it replaced. So what they do is they share the load. So the more belts we have, and the more pulley, the more torque we can generate on the belt, right? So basically, these are just the same as using multi-belt, but this would just be the multi-V belt. What determines the strength, of course, is what we put right here. So Anybody ever, cut a belt apart? What's that usually, what is that usually right there? Strings of, could be strings of metal, but it's gonna be like Kevlar or something like that, something that's real high strength threads running into there. So that right there is your strength memory. That's what's giving the belt the actual strength that it can have. Conveyors and conveyors. So anybody ever seen this? This is pretty cool. This is we call it a Delta robot. So, we had one on Long here one time. It's really cool. You jog it the same way, XYZ. Nothing is different, but here you got 3 arms that move around. Of course, this would be a standard 6-action robot. So what do we use conveyor belts for? Just to move things, right? Move material. That's all we use from one place to the other. I'm sure Amazon's got a ton of them. These are some really neat, different types of belts, groove belts, scoop belts, different types of belts. And then, it's very, very popular now to use, rollers. And the rollers can actually move around. I need to tell you that. This is not very long. Let me stop it. Conveyor belts, continuous moving band of fabric, rubber, and metal used to transport objects or material from one place to another. Longest belt, 61 miles in western Sierra. It runs from Morocco to the coast of South Africa. 61 miles. I don't know how long the belt is. There's a belt. It's not being used anymore because they're not making steel at U.S. Steel anymore in Fairfield. But it ran all the way from Birmingham Port. You know where that's at? You know where that's at? Where they actually, yeah, where the Birmingham, yeah. And then ran all the way to Fairfield. If you go down 15th Street, you go under that belt. So you know what I'm talking about? If you go down 15th Street, you go under the belt. So I don't know how long that thing is. I don't know how far it is, a straight line of shot. But 61 miles is a long way for a conveyor belt. They consist of rollers, drums that serve as platforms, spring rotate around a series of rollers, drive and idler tools. Material to be moved, placed on the belt, right? And the rollers move, mechanically advantaged. This would be for I wouldn't know how to calculate the mechanical advantage of those rollers. I wouldn't have any slightest idea because there's a lot of information we don't know. Normally we use the diameter of the driver and the diameter of the dump.
Something we use for most of the machines is drop off.
What's that?
Rollers and belts. The fold laundry. That's all I would use.
Oh, really? So I don't know where this conveyor belt is. This might be the one that runs for 61 miles. Well, the one that ran from Birmingham all the way up to Fairfield, it was living iron ore. Yeah, iron ore. They used to make iron out of it. It's red. Anybody ever see? They used to mine it here, but we drained them. Muskota Hill had several mines out there. That's what got Bessemer going, by the way. U.S. Steel built a glass furnace in Bessemer. I forgot what road you can still see. I can't remember which avenue it's on. It's the one that runs all the way out to Pullman, I think. So they were shipping iron ore, and it was in pellets, looked like marble. And then they'd bring them over to the ore yard, which was nothing but big old piles of ore. And we'd take our truck out there. When I was an electronic repairman at U.S. Steel, we had a truck, a real nice truck. And, We used to go over to the ore yard and do wheelies out there because it was just like riding on marbles. So nobody called us. I guess they could. So we could go off plant because our crew could go off plant. So we could go outside Fairfield. We'd go to the mines, and we'd also be able to go over to the ore yard where they had all the iron ore.